Terminator. This is a bit of a follow-up video from one I did last year on how much kill is enough, and I think the major outcome is that I think I might have had it wrong, and I'm going to sort of talk through my change in thinking over the last few months on how much kill is enough might be a different equation. So if we just think about the seed bank, because this is what it's all about. If we can maintain or get a seed bank, weed seed bank, as low as possible, that means that every season we've got less weeds growing, we've got less genetic diversity in those weeds and less chance of resistance. So smashing that seed bank down as low as possible is key to long-term sustainable weed control. So I guess the key thing is a lot of the main weeds in grain production are annual species. So there's a cycle, and basically the seed germinates, it grows, becomes mature, and then that plant produces a certain number of seeds to feed the seed bank. So what Seed Terminator is all about is interrupting that cycle and taking some of those seeds that have made it through to harvest and not let them become weeds next season. So if we just looked at the real fundamentals, so this is a very simplified case, an engineering view of weed science, or population dynamics, if you like. And basically we have a certain number of seeds here that start in the season. So we have, I've got the season number is I, and the number of seeds that start in the seed bank is SI. So if we assume there's no dormancy, which is not a true assumption, but just for the purpose of this example, say that every seed that is in the soil is going to germinate that season and become a plant, and the plant is PI. So we go from, so the number of seeds is the number of plants. So this is before we do any weed control application. So if we've got SI viable seeds, they become PI viable weeds. So if we do nothing, what happens is we have next year's number of seeds is the number of plants times the viable seeds per plant, which is NS. So I guess the underlying issue is that each plant wants to survive. It's evolved to survive. So it produces a lot of seeds per plant, and it does depend on the weed species. But the really prolific weeds have a lot of viable seeds per plant. So if we control not enough of those weeds throughout the season, we'll actually have more seeds in the seed bank next season than we started with this season. So SI plus 1, or the next season is worse or higher number of viable seeds than SI. So that is, in a nutshell, the main reason why weeds are such an ongoing prolific problem, and we haven't got to the bottom of it. So if we then say, right, I'm going to apply a certain amount of weed control, the main control method during the season would be herbicides in conventional or modern conservation agriculture. So we apply a certain level of control, so CH, that's the percentage control throughout the season, and the assumption is that we've just got this one rounded up number. It could be a number of different herbicide applications throughout the season, but if we just use a simplified numbering there to say that overall control is CH. So basically then, instead of having all the plants surviving, we have a certain percentage, or certain number, so we've got PIH surviving, which is the number of plants that germinate times by 1 minus the effectiveness of the control. Then we have a certain number of surviving, so the number of surviving plants produces a number of viable seeds per plant, the NS. So the total number of viable seeds at harvest is this SIH. So it's a number of seeds times by the surviving plants. So it looks more complicated than it is. It's just these is how many plants we got left over. That's how many seeds per plant, and this is the number of seeds. So if we were to do nothing else, this would be the number of seeds that enter the seed bank for next season and become next year's weeds. So that I guess that NS number is taking into account any predation or loss of viability for whatever reason. So it's how many seeds that are going to leave a plant and become a weed next year. So if we were to do nothing else, what we would have is this: the number of plants next year would equal the number of seeds per plant times by the number of plants in year one times by this herbicide control function. So, in an ideal world, what we want to do is bring that weed number down to 0. We got 100% control, but usually that's not possible. There's a whole number of reasons why herbicide application isn't 100% effective, and just the application process itself is mechanical, and plants can get missed with the spray application. Herbicide resistance is a factor. Also, just the dormancy of a plant. So if the plant germinates later than the application, then it's going to be missed. So we do have a proportion that gets missed. So if we said, well, what about if what is the amount of control that we need to make sure that next year's problem, so Pi+1, is actually better than this year's problem? So we're actually declining the seed bank. So all we need to do is just set the I+1 and Pi to the same, so that we can solve for what is the minimum level of control. And again, it's very simple. So the minimum level of herbicide control to make sure, so at that control level NS, this control level CH minimum, the population next year will be the same as this year. So anything higher than this will give us a declining seed bank. So it's obviously very, very important on the number of viable seeds per plant. So if a plant is very prolific in seed production and the viability of those seeds, then we need to get a much higher level of control to decline that seed bank. And I've just done a calculation here. So this along this axis here is viable seeds per plant, NS, and the minimum herbicide control to achieve a declining seed bank. So at low, so I guess at 10 plants per, so 10 viable seeds per plant, the control level is 90%, which makes sense. And then as you increase the number of viable seeds per plant, then it becomes increasingly more difficult. So, and remember that not all the weeds are going to be up and available to be sprayed at the time that you can spray them. So this is the overall control. So the end of the season, how many plants you've got left, and what control you need to have. So this graph here I've just got with a logarithmic scale, so it's a little bit easier to read. So as we go from 10 viable seeds per plant up to 20, we go from 90 to 95% control. 30, you're looking at 96.7% control, and 100 plants, we need 99% control or greater to tip the scale. So annual ryegrass, for example, typically can be 80, 100 to 150 sort of viable seeds per plant. So we need to be achieving in this 99% or above bracket in order to decline the seed bank. That's with herbicides alone. So where does the harvest weed seed control fit in then? So then once we get to the end of the season, we've got a certain number so I've just got that plot there. So once we get to the end of the season, we've got a certain number of plants with viable seeds, and then we have an opportunity there we can harvest them. If they're above the cutting height, they don't get threshed out, they're not shattered. If you can get them out of the rotor and onto the sieve, then we can control them with a harvest weed seed control measure and apply a certain level of control. And this CM level of control is overall, so it's how much you can get into the harvest weed seed control system and how much that system will kill. So multiply the two together. So then next year's problem becomes the same as the herbicide equation multiplied by this control level of the harvest weed seed control measure. So again, we can look at, well, what about the combination of non-chemical harvest weed seed control and herbicide applications would give us a declining seed bank. So again, we set the PI plus 1 to equal to the PI. So this year's plants is the same as next year's plants. So then we just come up with this equation here, which when we plot it, looks like this. So on the x-axis, we've got the in-season control or the herbicide control. And then on the y-axis, it's the minimum level of harvest time control in order to achieve a declining seed bank. So it does depend on the number of viable seeds per plant as per the herbicide only view. So if we've got 50 seeds per plant, then this would be the curve. So if we can achieve 95% control during the year, then we need to be getting 60% at harvest time. And then so anything more than that 60% is going to achieve a declining seed bank. So we want to be on this side of that graph. And then as the number of seeds per plant goes up, then we need to move further and further this way. So I guess it sort of demonstrates that, so the first part is that really herbicides alone, it's going to be a big task in order to get the percentages you need to get a declining seed bank. So it's an ongoing issue. You get a spiraling upwards seed bank, which means potentially higher risk of genetic diversity, which would have a potential for resistance. And just in general, you've got more weeds germinating season on season, so you need to be bringing in different break crops or different rotations to reduce those numbers. And when you add non-chemical harvest weed seed control, then you've got somewhat of a chance. So big viable seeds per plant crops are more challenging. You need to get higher proportions in season plus higher levels of harvest control, but it does give you a chance. Again, this is that same plot. So I guess this is a really simplified view, and there's a number of other factors. Dormancy, weeds do come up in cohorts throughout the season, different rain events. They've evolved to avoid herbicide applications like knockdowns. The viability, we've rolled it into that one number, so you might lose some seed viability over the summer with predation or other means. They might be on the surface and not able to germinate. And the number of seeds per plant is weed dependent, but it does depend on the growing conditions. So if we put the weeds under a lot of stress, then the number of seeds per plant might reduce, so it improves our chances. And we haven't included any herbicide resistance, so that is another factor altogether. It's just about maintaining the seed bank and getting good control. So if we just go back to this Excel sheet here, so we've looked at what you need to do as a minimum for herbicides alone, and then what the minimum would be for herbicides plus harvest weed seed control. And now we just look at different scenarios. and what that means from a overall control level and what happens to your populations. So I've got here 4 scenarios. So we've got the first scenario is no or nil harvest weed seed control. And on that scenario, I've assumed that we end up with 30% harvest control just because the harvester collects those seeds into the grain tank. Might not be quite that high, it might be more like 20%. But there is some capture in the harvester itself. Scenario 2, we're looking at a lower, so it's 73% kill of what goes into the device, and then 87% kill, and then 98%. And I've got 3 slides here just looking at how much. So there's capture, which is 60% in this slide. The next one's 80, and the following one's 95, multiplied by kill, and then what the overall control is. So then we look at a 10-year or 10-season, what happens to that seed bank ongoing, which is a really simplified thing. Obviously, you're going to grow different crops and different things are going to happen each season, but I think it's important to understand the fundamentals. If we can try and push down, spiral down the seed bank, then we can we can improve the scenario over time. So what you can see here is that with the nil harvest weed seed control, the numbers spiral upwards quite quickly. So I've started off at 10 plants per square metre. I guess that we can change that number and the proportions will be the same. So, but as you know, for year 4, we've got a blowout basically. If we apply 73% kill at 60% capture, it's a 44% overall control, which means that we can push that 4 years out to 6. And then if we go to 87% kill, then we're looking at potentially 8 years. And then 98%, we're looking at, that might be 12 years or something. We haven't actually got that far to get to the same sort of blowout scenario. So yes, it doesn't seem like a big change in overall kill here, but it does result in a significant change in the ongoing seed bank. And so I guess the question is why? Well, we actually need to possibly look at the opposite of the control. We need to look at because it's easy to think, we're not talking big numbers between 87 and 98. It's 11% at that level. But if we went the other way around and said, 1 minus 87 is 13% versus 2%, so we're talking more like 6.5 times as many seeds that we've got in our hands that we're letting through. So that's sort of why it makes a big difference. And this is the least different scenario. If we then move to a 80% capture, and then the same number of kill numbers, we see a different scenario. So we're looking at the nil is obviously still blowing out. I had this number at 20 on the other one. The 73% control, it's going upwards, but it's not blowing out really quickly. And then the 87 and 98% control are both spiraling down into control. But there's a big difference between how fast they're doing it. So this percentage here is looking at, how much better or how many more seeds there are with a nil control versus the 73. And then this one is how much better how much more the 73 seeds is compared to the 87. And this one's how many more seeds the 87% control has compared to the 98%. So in year 1, you've got 41% more plants. Sorry, the second season, you've got 41% more plants growing. And yet the overall control's only 8% different. So that is like and then that compounds, so it's a compounding interest. So over time, over a 10 season time frame, you've basically got 20 times as many viable plants after 10 years with an 87% control than you do with a 98% control, even though you're only getting 80% into the mill or the harvest weed seed control device. So, you know, I think this sort of shows that we can get the populations down with both levels of control, because there's definitely a massive cost increase to go from 87 to 98%. But if you factored in some herbicide resistance in here, the risk of herbicide resistance when you've got 20 times as many plants is way higher. And so if we got to 95% into the front and then same levels of kill, the scenario is even more highlighting. So we're looking at 4,000 times as many over time, over a 10-year period. But you can sort of see that if you get those high proportions in the front or into the mill, then high levels of kill are going to drop that seed bank really, really quickly, and certainly 30% or 40% earlier. So I guess that's, this is an evolving conversation, but I think in my mind, the key takeaway is that we need to think about kill in terms of survival, not in a percentage, because it's easy to look at 97 or 98 and 87 and think, well, there's not that much difference in there. But if you look at percentage of survivors, and these are survivors that we've got in our hands, we've got, you know, we can do something with them, and we're just trying to save some money in terms of power and wear, for example, we're potentially compromising ourselves. And I guess the other thing is that why are those last few percent surviving? Is it because they are lighter and stronger? Is it a case of a low dose experiment, just like using low doses with herbicides? If we use low doses of mechanical control, are we potentially breeding resistance to mechanical control? I don't know the answer to that, but it's definitely food for thought, and I'd love to hear everyone's feedback. I guess the other part of this equation is, well, if we looked at these three scenarios, they're all very different, and this could be, you know, cutting that bit lower to get more weeds in the front, and we know that the root cause of wear in the mill is soil, particularly abrasive soil types. So the more soil in, you know, it makes a big difference to wear, and that's a cost. But again, if we cut it lower and go from 60 to 80%, there's a massive change in the population dynamics. So where I was sort of suggesting that be careful how high you cut because I don't want you to wear out your mills too early, I think we need to change that message and say, let's go hunting for these weeds, because the benefit's going to far outweigh the cost of wearing steel faster, because you're capturing more, which means you can kill more, which means you can drive the population down much faster. So, yeah, I guess it's very similar to this low dose experiment with kill, but you know, if we cutting lower is like adding a higher rate of chemical, and so is pulverizing the material more. We are applying a higher rate of chemical. It's going to cost more, but in the long run, if we're declining the seed bank, I think it's worth it. Thanks, guys.